Okay, here we go again. Chemistry 3202, course overview, review. This is on Unit 2, Section 2, Lesson 1, the special nature of water, KW. This information is dealt with on page 564 of your textbook, and there's a few questions there on page 566 that deal with what we're going to do in this session. Here are the outcomes for this lesson. We want to consider the special nature of water, the ability for water to auto-ionize with itself. And what we mean by that is we learned in the last couple of lessons about the Bronsted-Lowry definitions of acids and bases. And we found out that water is one of these special acids and bases that are considered to be amphoteric. In any given condition, water is capable of giving away a hydrogen, acting as an acid, or it can accept a hydrogen and act as a base. So what we're saying then is, well, what happens if we have two water molecules that are in the same container? Wouldn't it be possible for one of these water molecules to give away a hydrogen and act as an acid, and at the same time another water molecule could gain that hydrogen and act as a base? So we call that process auto-ionization. And the idea behind it is that 1 in 10 million or 1 in a billion or so actually do this. And what we notice is that we can write a reaction for the auto-ionization of water. And we can show that in this case, we can see that we have two water molecules here. And these two water molecules, one is going to donate its hydrogen and act as an acid, while the other one is going to accept that hydrogen and act as a base. So we refer to this as the auto-ionization of water. And what we end up seeing, of course, is the production of H3O plus and OH minus. And we would refer to the H3O plus, obviously, as the conjugate acid, and the OH minus would be the conjugate base. Now, some measurements can be taken here, and we can find that when this happens under room temperature at about 25 degrees Celsius and standard temperature pressure here, what we're noticing is that the concentration of H3O plus can be measured to be 1 times 10 to the minus 7 moles per liter. And likewise, because it's a 1-to-1 ratio, that the concentration of OH minus is also going to be 1 times 10 to the minus 7 moles per liter. Now this 7 should have a little bit of meaning here now, because what we're doing is we're using pure water and seeing that pure water can auto-ionize itself. And the pH, we're going to learn this later on, the pH of pure water is a neutral 7.0. So this number has some significance as we start getting into some pH calculations and things like that. All right, so with this said, assuming that this does happen, that water can auto-ionize itself, and assuming we can measure the concentrations of pure water to be 1 times 10 to the minus 7 H3O plus, and OH minus is going to be 1 times 10 to the minus 7, let's do an equilibrium expression here. And we're looking at this particular equilibrium expression. Hold on now. And we can write it as products over reactants. Okay, let me just get rid of it all. There we go. Okay, we can write this as products over reactants. And you notice here that products over reactants, we end up getting a KW being H3O plus times OH minus. Now you might say, well, what happened to the water? Where did the water go? Well, the water is in the liquid state. And remember, we do not include solids, pure solids or pure liquids in equilibrium, because their concentrations don't change for the most part. They're 100% pure, and they'll be 100% pure before and after. Their concentrations do not change. So we do not use the H2O. So in this case, the reactants, we don't have any because they're pure liquids. So we just omit them from the equilibrium expression. And because we're doing this for water, we give it the little subscript here, KW. And that's the equilibrium expression for water. So it's simply going to be H3O plus times the OH minus concentration. We put our values in for the ones that we have here, 1 times 10 to the minus 7 and 1 times 10 to the minus 7. We work it out. And we end up getting this nice number, 1 times 10 to the minus 14. Now, what's the significance of minus 14? Well, if we look at this value over here, that's a 0.00013 zeros and a 1. That's 1 times 10 to the minus 14. That's a very, 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 very tiny number. And because it's so tiny, so much less than 1, this equilibrium lies far, far, far to the reactant side. So what we're saying then, if we look at our equation up above, is that, yeah, this reaction, for the most part, really doesn't want to go forward that much. The little bit of forward we do get, 1 times 10 to the minus 7, that's a really insignificant amount. That's a very, very tiny amount. So what we're saying is that water can do this, but because the value is so tiny here, the equilibrium value, it doesn't do it a lot. Right? It's a very tiny value, so the reactants are favored heavily here. Okay? And what we end up with is this nice expression for the equilibrium expression for water. Kw is the H3O plus concentration times the OH minus concentration. And as long as we're at 25 degrees Celsius and we have pure water, then this value holds, 1 times 10 to the minus 14. That's a very special number. Okay, we can do some calculations here now based on other solutions that we would have, because if we take hydrochloric acid or sodium hydroxide or some other acid and base and put it in water, then not only are we going to get a source of hydronium from the hydrochloric acid, but we're also going to get a little bit from the water. Likewise, when we put sodium hydroxide in water, that not only do we have the sodium hydroxide to contend with for the hydroxide concentration, we're also going to get a little bit from the auto-ionization of water. So we're going to use these calculations or these ideas to calculate the hydronium ion concentration and the hydroxide ion concentration when we put 0.15 moles per liter of hydrochloric acid solution. We want to be able to measure each of these. All right. So what we're looking at then is we're saying HCl is a very strong acid. It's going to be 100% ionized. So every last bit of the HCl is going to move forward here and produce H3O plus and Cl minus. So when we look at this, we say, all right, not a problem. We know the concentration of HCl is 0.150 moles per liter. So what we're saying is, because it's such a strong acid, the H3O plus concentration is going to be quite large. And we can actually calculate it here, and we say the H3O plus concentration is basically the same as the hydrochloric acid concentration, because again, every last bit of this stuff would break down. So the concentration of H3O plus in this case would be 0.15 moles per liter. If you want to put that in perspective, we can, if you want to put that in scientific notation, just to compare the value that we get from water, this would be 1.5 times 10 to the minus 1 moles per liter. That's a lot bigger than 10 to the minus 7. So the amount of H3O plus from the hydrochloric acid is much, much more significant than the amount of H3O plus that would come from water. All right, so there we go. Now the question would be then, well, what about the hydroxide ion concentration? Well, from this equation, there is no hydroxide being produced. So we would go to the conclusion then that if there's any hydroxide in this container at all, it must be coming from the auto-ionization of water. So based on that, we can now do a calculation and say, okay, any amount of OH minus is going to be from the water because of the auto-ionization aspect, okay, because water is present in this container as well. Okay, so there we go. So what we want to do then is we want to be able to calculate the OH minus concentration based on this equilibrium. So what we're going to do, let me just see if I can, there we go. We know that Kw is going to be H3O plus times OH minus. We know the Kw value here now. It's always going to be this, 1 times 10 to the minus 14. We now know the overwhelmingly amount of H3O plus. There's a significant amount of that from the hydrochloric acid, so we're going to use that great big value there, 0.15. The only thing we don't know is the OH minus. So what we do is we simply divide both sides by 0.15, and lo and behold, what do we get? Let me just reveal it this way. There we go. So in this case, we're going to simply divide both sides by 0.15, and we get 6.6 times 10 to the minus 14 moles per liter of hydroxide. And that's not very much, is it? 10 to the minus 14 is a very, very, very tiny amount. And that makes sense because the only source of that is from the water, which is producing a very tiny amount anyways. Now, the question always comes up is, sir, I can't get this number on my calculator. I can never get that number on my calculator. The problem is you could be doing something wrong here with your calculator itself. Now, when you start using this 10 times 10 to the minus 14, it's very important that if you're going to put it in on your calculator, make sure you always put brackets around your exponents like that in your calculator. Let me show you. I'll share my calculator with you. Okay, so here we go. You should be looking at my calculator here now. I'm going to turn it on. And when I turn it on, I'm going to put in my values. So I'm going to say bracket 1.0 times 10 to the minus 14 bracket divided by 0.150. And I hit enter. And I got a mistake. Okay, let's try this again. Okay, bracket 1.0 times 10. Here we go. To the exponent minus 14 bracket divided by 0.15. There we go. Okay, 6.667 times 10 to the minus 14. All right, a couple things I have to point out here is the exponent sign right here, right, to the power of minus 14. This is the minus sign here, not the subtract, right, the minus sign, and you get that value. Okay, that's one way to do it. Another way we could use your calculator to do this is we could use the exponent button itself, and that's this button right here. All right, so I could go 1.0, second function, exponent, negative 14, divided by 0.15. And there we get the same answer. Now you notice I didn't have to use my brackets here because I used the exponent feature, which means the same thing as times 10 to the minus 14. So very important that you choose one way or the other to do this. But if you're using the times 10 to the power, then make sure you put brackets around your values. Okay, and I'll do another one for you now in a sec. Okay, so here we go. So in this case, what we're looking at is the idea that H3O plus is so much bigger than this value. OH minus is very, very, very tiny. So the amount of OH minus is almost insignificant. In fact, it is insignificant compared to the H3O plus. And this should make sense because, after all, hydrochloric acid is an acidic solution. So the H3O plus, that what makes it acid, is in a very large concentration. That's why it's an acid. Okay, the OH minus is what gives it its basic properties. This is not basic at all. This has operational acid properties, right? Blue litmus red, tastes sour, reacts with acids to produce hydrogen gas, etc. And this is why, because this is a very large number. Let's look at another example. Here's another one. This is one we want to calculate the hydronium and hydroxide ion concentrations for some calcium hydroxide solution. All right, so what we say is, all right, no problem here. We're looking at calcium hydroxide right here, and we're saying that calcium hydroxide is an ionic compound, so it's going to be 100% dissociated. It's going to break down into its ions. And we know what the initial concentration of the calcium hydroxide is. It's 0.00150. So this is going to be a base. It's producing hydroxide. The hydroxide ions are going to be quite large in concentration. The hydronium, which is only coming from water, should be quite low. After all, this is a base. It's going to have basic properties. So let's have a look at it. Now, what we have to be careful with in this one is that this is calcium hydroxide. So there's a 2-to-1 ratio for hydroxide ions to calcium hydroxide. So we have to take that into account. And we look at this and we'll say, okay, the hydroxide ion concentration is going to be 2-to-1. right? 2 to 1, there's that 2. We're going to get twice as many hydroxides as we had calcium hydroxide, so we plug it in. This big M refers to moles per liter. It means molarity. It's simply another way of expressing concentration, moles per liter. So we put our values in and we get 0.00300 moles per liter of hydroxide, twice as much, because that's what that says, twice as much. We'll proceed to do our calculation and we'll say, okay, now we know what the hydroxide is. The hydronium is going to come from the water. We do our little expression, Kw is H3O plus times OH minus. We plug our values in here. Let me just do it this way. Okay, we rearrange. H3O plus is going to be Kw over OH minus, and then we plug our values in, and lo and behold, we get 3.3 times 10 to the minus 12. Let's try that on our calculator once again. Okay, I'm going to clear this. I'm going to say bracket 1.0 times 10 to the power negative 14 bracket divided by 0.3. 0.03, wasn't it? And there we go. 3.3 times 10 to the minus 12. Again, don't forget your brackets. Okay, so 3.3 times 10 to the minus 12. So this is the hydronium concentration, and it's not very big. It's 0.0000003, right? There's 11 zeros in front. Very tiny amount. Should make sense. We don't want that there because obviously this is a base. This concentration is the same as saying 3 times 10 to the minus 3 moles per liter. So the hydroxide ion concentration, although it's not large, it's a lot larger than this, right? It's almost a factor of 9 times larger, right? Very, very significant compared to this. This is insignificant, okay? So there we go. And that should make sense because, after all, it's a basic solution. The hydroxide ions is what's giving it its basic properties, its ability to be right back, right? Bases turn red litmus blue. They're slippery. They're bitter. They neutralize acids and things like that. This guy right here, the H3O plus, is tiny. It's insignificant. Its only source is from the auto-ionization of water. It shouldn't be there anyways because this guy is a base. And there we go. Okay. Here's another example. It says calculate the hydronium ion concentration if you've got 2 grams of sodium hydroxide dissolved in 250 mils of water. Okay, so here we go. This is an ionic compound, so the sodium hydroxide is being dissolved in water. It's going to dissociate 100%, very highly soluble. And what do we know here? Well, we know the mass of sodium hydroxide. We know the volume of the solution. What we're looking for is the concentration of OH minus. Okay, we need the molar mass of sodium hydroxide. And you guys all know why we need that, because we need to find the number of moles. And there we go. The number of moles of sodium hydroxide, mass over molar mass, so it's going to be 2 grams over 40 grams per mole, and we get 0.0500 moles of sodium hydroxide. All right. Now because that's 100% dissociated, the concentration is going to be the number of moles divided by the volume. So 0.0500 moles and 0.2500 liters, we get 0.2 moles per liter of sodium hydroxide. And again, because that's 100% dissociated, we know the concentration of hydroxide is going to be the same as sodium hydroxide. It's a 1-to-1 ratio. Every last one of these sodium hydroxides is going to be dissociated. It really doesn't exist like this. It really exists in water as a dissociated ion pair. There we go. Okay. Now, can we calculate the hydronium? We sure can, because we now know that any hydronium that's present is going to be due to that little bit that comes from the water. And there we go. So Kw is H3O plus times OH minus, and we know what that equals. Okay, 1 times 10 to the minus 14 divided by 0.2 moles per liter. And lo and behold, we don't expect a big number because after all, this is a base. The hydroxide ions should be much more concentrated than the hydronium. And there we go. It's 5 times 10 to the minus 14 moles per liter. Now you may want to check this on your calculator to see if you can get the same answer that I have. And if you can't, you better check with one of your teachers who knows how to use a graphing calculator, or one of your friends, so that you can get these answers, right? These are too easy. Easy marks on public exams. There's always one of these as a multiple choice or some nature where you have to calculate hydroxide, knowing hydronium, etc. So make sure you know how to use your calculator. There we go. And once again, we didn't expect this number to be very big because after all, this is not an acid. This is a base. It's a base. So the concentration of hydroxide is much larger. That's 2 times 10 to the minus 1. That's why it has basic properties. The hydronium is 10 to the minus 14, very tiny. Okay, here's another sample. This is a sample of what happens when we have a weak acid. All right, everything we've been doing up to this point has been strong acids, which are 100% ionized, ionic compounds that were 100% dissociated. What happens when we get a weak acid where it really doesn't want to ionize? It does not want to produce H3O+. So what do we do there? Well, here's an example where we use hydrogen fluoride and say, okay, that's a weak acid. What's going to be the hydronium concentration and hydroxide concentration when we put 0.2 grams of this stuff in 100 mils of water? So here we go. Okay, now HF is a very weak acid. When it reacts with water, only 7% of it wants to move forward. Now the question is, where did I get that value? That value comes from the acid-base strength table. Look up hydrogen fluoride or hydrofluoric acid, and beside it would be its percent ionization. So this particular reaction is saying that only 7.8% of this stuff wants to move forward. So I should have a double arrow here because it's going to be reversed for the most part. And the question would be then, well, what's the H3O+ here? Okay, shouldn't be a problem. We know the mass and volume of the hydrofluoric acid, okay, or the hydrogen fluoride. And what we want to do now is calculate the concentration of that. So the first thing we need is the number of moles, mass over molar mass of HF, right, 0.2 divided by 20.01. And we get 0.009995 moles of HF. We want to figure out the concentration of that. Okay, so it's going to be the number of moles divided by the volume in liters. And we get 0.0100 moles per liter of HF. Now here's where it's different than what we did with hydrochloric acid. Let's just go look at our hydrochloric acid sample again. Right here. In hydrochloric acid, we said it was 100% forward. So in this case, we said every last one of these HCl's is going to break down. So the concentration of H3O+ was equal to the concentration of HCl because it was 100% reacted or ionized. In this example, it's only 7.8%. So I have to do an additional calculation here. And what I have to do is right here, I'm going to say the concentration of H3O+ is equal to the percent ionization or the percent reaction times the initial concentration of that acid. So in this case, it's going to be 7.8%. We want to get rid of the percent, so we divide by 100. And we get 0.00078 moles per liter of H3O+. Okay, we just found our H3O+, our hydronium. That's done. Okay, this is an acid. What we need to do now, of course, is figure out the hydroxide that comes from the water. Okay, so the hydroxide, there's none coming from the HF. It has to be coming from the auto-ionization of water. And of course, we just figured this out. We know that Kw equals OH times H3O+. So OH minus is Kw divided by the H3O+ that we just found up above. We put our values in, so it's going to be 1 times 10 to the minus 14 for Kw, 7.8 times 10 to the minus 4 for the hydronium. And let's do another calculator share here to make sure to see if you guys want an extra little bit of assistance here. Okay, and here we go. Let me just share this with you. And here we go. So it's going to be bracket. Oh, let me turn it on first. Clear that. Bracket 1.00 times 10 to the power negative 14 bracket divided by bracket 7.8 times 10 to the power negative 4 bracket. Enter. So it's going to be 1.282 times 10 to the minus 11. And again, make sure you can do that on your calculator. This is too easy to lose marks for not knowing how to use your calculator. Okay, so we put that value in there. 1.28 times 10 to the minus 11 moles per liter. What we're looking for here is 3 significant digits. We got 3 digits right here. Even though this is 4 digits, we're multiplying and dividing, so we're always going to go to the least number, 0.200. So 1.28 times 10 to the minus 11 moles per liter of hydroxide. Minus 11 versus minus 4, although the numbers are starting to get closer together, this is still quite significant compared to this. This is like 10 zeros in front of the 1. This guy only has 3 zeros in front of the 7. So this guy is very much, it's still an acid. So the concentration of H3O plus is still quite larger than the OH minus, because this guy is definitely going to have acid properties, right? Acids, base, blue, red. It's going to do everything that acids do. Okay, there we go. Okay, what is all this then? What's the significance of what we're talking about, hydroxide versus hydronium? Well, in every single acid or base, remember the idea behind it is that water is always present, and water is always going to be a source of these ions. Now, depending on whether we have an acid, in which case the H3O plus is going to be quite large, the hydronium is going to be present, but it's going to be in very tiny quantities, comparably. And likewise, if we have a base, then the hydroxide ions are going to be quite large in concentration. The hydronium are still there, but they're going to be there in quite small quantities, insignificant for the most part. And what we're seeing is that there's a give and take for each direction. Now, I'm not sure how clear this is going to be for you guys, but this is a great big greater than sign, and this is a great big less than sign. So what we're saying then is when something is acidic, the concentration of H3O plus is big, the OH minus is very tiny. Okay? As we start going from acidic to more neutral, the concentrations of H3O plus and OH minus are starting to get closer and closer together. And of course, for neutral water, for pure water that's neutral, this value equals this value. It's 1 times 10 to the minus 7. And as we start going over to the basic side of the spectrum, we're noticing that as we start going over, the H3O plus is beginning to get smaller and smaller and smaller as we move to the base side, whereas the OH minus is getting larger and larger and larger as we go to the basic side. So there's a trade-off. If one is large, the other is small. And as we start moving towards the neutral, that's where the concentrations start coming together. Okay? So we always have both of them present. Depending if the one is in larger quantities or lesser quantities, that's going to determine whether or not it's acidic or basic. There we go. Don't forget to take advantage of our online tutors and all the online material that we would have for you guys, the online tutoring, the online course material, public exam materials, and whatnot. Make sure you take advantage of it. If you have any questions, drop me a line in the discussions, and I'll try and get back to you in the next session. Okay, bye-bye.